continue our conversation about the different forms of energy. So far, we've talked about kinetic energy, the energy of motion, and that the two factors of kinetic energy are mass and velocity. If I want to change the kinetic energy, I really only have one way of doing that, and that is changing the velocity. So the formula for plain kinetic energy is 1/2 mv squared, using those two factors. The change in kinetic energy is going to be represented by changing the velocity, or 1/2 k m v, delta ke is equal to 1/2 m v squared minus v naught squared. Then we talked about potential energy due to gravity, and it's the energy an object possesses because of its vertical separation from the Earth. The more I make a separation, the more potential energy an object has. Again, I'm not going to change the mass, but I am going to change its vertical position. And then we went through the derivation of both of those, and let me encourage you again, you should know those derivations. If I say to you on a test, give me the derivation for the change in gravitational potential, you ought to be able to do that for me, or give me the derivation for the change in kinetic energy. So we went through both of those, and now we need to jump into an example of how we use the change in potential energy. So please look at 8.4. A 400 kilogram roller coaster starts 48 meters above the ground and is 3 meters above the ground at the end of the ride. Calculate the change in gravitational potential energy of the roller coaster. Now we've been given the formula delta PEG is equal to mgh. But I also want you to see that I could write it as mg. My height is the change in vertical separation. I could also make it y minus y naught if I don't end up on the ground. Typically, they're going to be on the ground, but if they're not on the ground, then you can go ahead and use the y minus y naught. So we've got our roller coaster. I'm going to draw a little roller coaster here. Very boring roller coaster. And let's get this thing all the way drawn because I do not want anything to happen to the people on my roller coaster, so I need to have nice supports for them here. And we'll do it like this and this and this and this and this and this. Okay, so my roller coaster is supported. And I've got my cart up here with my people in it. And that's my initial position. And my initial position is 48 meters above the ground. And then my final position here, we're going to talk about roller coasters actually a couple of times in this chapter. And by the way, their hair's all like this because they're scared and because it's windy. Their final position is 3 meters above the ground. And we are told that this is 400 kilograms. So that's its mass. And of course, we know that G is 9.81 meters per second squared, in this case because I'm in the metric system. So delta PEG is going to equal mg y minus y naught, which is the mass, 400, times 9.81, times my final position, which is 3, minus my initial position, which is 48. And when you do the math on that, you end up with a negative 180,000 joules. What does the negative tell you? You remember from our initial lesson on work, negative means that energy has been taken out of the system. I had a truckload of potential energy up here. I have very little potential energy down here. So my change in potential energy is negative because I have lost or have lessened the energy in the process. Let's talk about where my units came from. We'll just go ahead and do MGH because remember, Y minus Y naught can be scooped together as just one unit. So my mass is kilograms, and my acceleration due to gravity is meters per second squared, and my height is in meters. So I have kilograms meters per second squared times meters. I have a Newton times meter, which is a joule. And again, remember that the negative is just as important a part of the answer as the quantity itself. All right, so that's going to be one where we actually use the Y minus Y naught. That doesn't show up very often. Just wanted you to be aware that that's one way that you can do it. The next one, a 100 kilogram cart is pulled 100 meters up a 20-degree incline. What is the change in potential energy due to gravity? So I'm going to make my drawing. 20 degrees, by the way, is not very much, and I'm making this probably steeper than I need to. But my cart is here, and my cart is 100 kilograms, and it's being pulled up the incline 100 meters. And all they're asking for is the change in kinetic energy. They're not asking for the work that's being done in this. So all I'm worried about is how much kinetic or potential energy am I changing, the change in potential energy, sorry. This is 20 degrees. So I need for delta PEG, I need my mass, okay, got that, times acceleration due to gravity, okay, got that, times the height. That seems to be missing here. This would be the height. If it starts down at this position on the ground and ends up at this position above the ground, that's my height, but I don't have it. I want you to pause the video for a moment and see if you can figure out a way that I can get this quantity, my h. You actually know how to do it? See if you can dig that up. Okay, hopefully what you came up with was I can use my trig function. I am looking for the opposite, because I have a right triangle here, I'm looking for the side opposite my 20 degrees. So my height is simply going to be 100 sine of 20. So what I really have then is the sine of 20 is equal to the opposite, which is h, all over the hypotenuse, which is 100. I move that over here, and that's how I got my height is equal to 100 sine of 20. Well, now I can plug all that in, and I have 100 kilograms times 9.81 meters per second squared times 100 sine of 20, and I end up with 33,600 joules to 3 sig figs. Okay, those are actually kind of straightforward, but be careful with the homework because in the homework, they're going to be having you convert your kinetic energy to potential energy or your potential energy to kinetic energy because that happens all the time. As I'm going down this hill, my potential energy up here is being converted all the way down to an increase in kinetic energy. So what is being lost by potential is being gained by kinetic. They're going to be two sides of the same coin with that one, and they will go back and forth with each other. Just going to introduce right now, we're not going to do any problems with this, but I'm going to introduce the elastic potential energy, which you'll remember is the potential energy of a spring or anything that is elastic. It's the potential energy of a material that stretches or compresses. Okay, now the potential energy of the spring depends on the length of the, and I'm going to use the word compression, but it could be either one. So every time I say compress, know in your head that I could compress it or expand it. It depends on two things. It depends on the length of compression. So I want you to be picturing a spring. How much potential energy I am putting into it depends on how much I am compressing it. If I only compress it a little, I only have a little potential energy. If I compress it a lot, I have a lot of potential energy. Think of a slingshot. If I pull the slingshot back just a little bit, I'm not going to get my rock to throw very far. If I pull it back very far, then I'm giving it a lot of potential, and I'm going to be able to get the rock that's in the excuse me, that's in the sling to move a lot farther. So the length of the compression is one, but also the shape of the spring, if I'm talking about a spring. So a quality of the spring affects my potential energy, and how much I compress it affects potential energy. Where does the potential energy of a spring, of a compressed spring, come from? How do I build potential into the system? I build it from the work it takes to compress the spring. And what I'd like you to do is at the very bottom, I don't know why I didn't make a whole big deal about this, because it really is a big deal. This is all based on Hooke's law, which says the force of compression No, you know what? I'm going to give it to you more scholarly. That was going to be my wording for it, but I like the scholarly wording of it. The size of deformation. How much did I compress or expand it? The size of the deformation, and that's why I like this, because it's generic to either compression or expanding. How much did I deform my spring? Did I stretch it out? Did I compress it? Is directly proportional to the deforming force. So the more force I put in, the more deformation, the more deforming of my spring I'm going to have. More force, more compression. More force, more expansion. That's the whole foundation of how a spring scale works. It works because you're applying force to it. The more force you apply, the heavier the weight at the end of the spring, the more the spring is going to deform. And it's going to measure it exactly that way. All right, and then on the next page, we're just going to get into the derivation for this. I'm going to do this briefly. This derivation is a little bit trickier than the other ones. So actually, I'm going to hold off on this because I kind of suspect that in our class tomorrow, we're not going to get any farther than what I did. So I'm just going to quit here for you guys. You're going to have a nice short day today compared to yesterday, which was a little bit longer, and the day before very, very long. So let me just tell you that your homework for potential energy due to gravity is 23, 25 through 28. So for this, your homework is 23, 25 through 28. But for 26, just do A only. You don't have to do the rest of that. A only. All right, there's not a lot of homework for these. It's just broken up into small chunks. But make sure that you're keeping up with them. And again, this homework is going to relate potential energy due to gravity to kinetic energy. So you can be very comfortable going back and forth between the two. Know that that's an option for that. All right, let me know if you need anything. Have fun with this.